Welcome to the deep dive. There's this incredible buzz around the moon right now, isn't there?
Oh, absolutely. It feels different this time.
Yeah, it's not just the big government agencies anymore. We're seeing a real new space race, but with private companies jumping in, competing fiercely to land on the moon.
It's a fascinating shift. High stakes, high rewards, potentially.
And that brings us to our focus today. There was this recent event, pretty public. The second attempt by the Japanese company is Space to land their Resilience lunar lander June 5th, 2025.
Right. And it didn't quite stick the landing, unfortunately.
No, it didn't. So in this deep dive, we want to unpack what happened there, the specifics of that failure, but also zoom out a bit. Look at the bigger picture of these private lunar missions. The successes, yes, but also the setbacks.
Because there have been quite a few of both recently.
Exactly, and explore this whole idea of a commercial lunar market. What does all this activity, these crashes and successes actually mean for space exploration going forward? Okay, let's get into it. There's definitely more here than just, a lost signal.
For sure. It's a real snapshot of this challenging new frontier. The moon is proving just as tough as ever.
So let's start with Resilience. The mission itself, it kicked off back on January 15th, 2025. Launched from Kennedy Space Center on a SpaceX Falcon 9.
Pretty standard launch vehicle these days.
Right. But the route wasn't standard.
Hmm.
Space chose this longer, much more fuel-efficient path. It looped around Earth, did a moon flyby in February.
Saving fuel, stretching the mission capability.
Yeah, and then went way out, like 1.1 million kilometers into deep space before finally settling into lunar orbit. Why that complex route? It seems counterintuitive, maybe?
Well, it's all about efficiency, especially for commercial play. Every drop of propellant saved means more payload capacity or just lower mission cost. It's a calculated trade-off, time versus mass.
Makes sense if you're trying to build a business case.
Exactly. You have to be smart with resources.
And
It shows they're thinking strategically about the economics, not just the engineering feat.
And Resilience was packed. It wasn't just a tech demo. It had 6 commercial payloads. There was that micro rover, Tenacious, from ISpace's Luxembourg team.
Intended for exploration, sample collection,
Yeah.
ambitious stuff.
Yeah. And a radiation probe from Taiwan's National Central University. But also some more unusual items, like a Gundam alloy plate
Right, the pop culture element.
and a UNESCO memory disk, plus this Moonhouse artwork. It's this mix of science, commerce, culture, all in one lander.
It really is. It reflects this broadening view of the moon. It's not just flags and footprints anymore. It's
Yeah.
potentially, a place for business, for data, for cultural expression.
A very 21st century payload manifest.
Definitely shows the diverse interests now pointing moonward.
So we have this carefully planned mission, efficient route, diverse payload. Then comes June 5th, the landing attempt. Target, Mare Frigoris, the Sea of Cold.
A relatively flat area chosen to make landing, well, easier, in theory.
In theory, but during the final descent, communication was lost. And ISpace, they had to call it, mission off.
A tough call, but necessary when you lose telemetry.
And the data they did get is chillingly precise. They lost the signal when the lander was about 192 meters up,
Just a few hundred feet.
but descending at 42 meters per second. That's fast.
Extremely fast for that altitude. Way too fast.
And they estimate it hit the ground just 5 seconds later. That rapid sequence, what does that suggest to you from an engineering standpoint?
It screams loss of control, specifically deceleration failure. The braking thrusters either didn't fire correctly, didn't fire long enough, or the system didn't know when to fire them properly. But the failure was clearly abrupt, right at the critical moment.
And that precision telemetry, right up to the end. That must be vital for figuring out what went wrong.
Absolutely vital. Heartbreaking, yes, but invaluable data. It lets engineers pinpoint the failure point. They know exactly what the lander thought was happening versus what was happening up until 192 meters.
And we got visual confirmation later. NASA's LRO, the Lunar Reconnaissance Orbiter, spotted a new crater, 16 meters across.
Yeah, confirmation of a hard impact. Not far from the target, about 280 meters south, 230 east, something like that.
So, not wildly off course, but definitely not a soft landing. Which brings us to the crucial part, the why. What did ISpace find?
They traced it to hardware, specifically the laser rangefinder, the LRF.
Okay, the thing that measures the altitude.
Exactly. It's supposed to tell the lander precisely how high it is. But the LRF was apparently slow to provide good, valid altitude data. It didn't kick in properly or quickly enough.
And without accurate altitude.
The lander couldn't calculate the right time or thrust level to decelerate. It was essentially flying blind in that final critical phase regarding its height. Didn't hit the brakes effectively because it didn't have the right info.
That sounds fundamental. Why would the LRF be slow? What could cause that?
Space narrowed it down to four main possibilities. One, maybe the lunar surface right there was less reflective than expected. The laser needs a good bounce back. Two, the angle the laser hit the surface might have scattered the signal. Three, maybe the laser itself on this specific lander wasn't quite as powerful as needed. Or four, the spacecraft itself wasn't oriented quite right or stable enough at those high speeds for the LRF to lock on.
So, several potential hardware or environmental interaction issues. They also considered radiation damage, but thought it was less likely.
Yeah, less likely based on their analysis so far. The focus seems to be on the immediate performance of the sensor and its interaction with the environment and the lander's dynamics.
And the kicker is, this was their second attempt. The first one, Hakuto Mission 1 in April 2023, also crashed.
Right, but that was different. That was a software issue.
A software glitch, yeah.
Yeah,
It
yeah.
miscalculated altitude because of how it handled data crossing over a crater rim, right? Made it think it was at the surface when it was still 5 kilometers up.
Exactly, so it just stopped thrusting and fell. A completely different root cause, even though both ultimately involved incorrect altitude determination. One software logic, one hardware performance.
And this resilience lander actually had a new LRF model because the supplier for the first mission stopped making the old one.
Which adds another variable. Was the new hardware adequately tested for all lunar conditions? These failures, painful as they are, really drive home how complex this is.
It really does. What's fascinating, as you say, is how they learn. You fix the software, then you run into a hardware issue. It's like whack-a-mole almost.
Well, it is iterative learning,
Yeah.
and that's crucial. These aren't just failures, they are data points. Expensive data points, granted, but essential for figuring out how to do this reliably. The hardware versus software distinction is key. It shows they're learning and adapting, not just repeating mistakes.
It just highlights what experts like Namrata Goswami say. Landing is extremely difficult, especially on the lunar surface. Failures aren't outliers, they're part of the process.
Absolutely. Space technology needs that proof of concept, that real-world testing, and the moon offers a harsh test bed.
Now, some people might look at these private attempts and say, see, they're not ready. Governments did this decades ago. But that's not quite fair, is it?
Not really. If you look back at the early US and Soviet missions in the 60s, there was a lot of hardware ending up as new craters on the moon before Surveyor 1 and Luna 9 finally succeeded.
Right. Lots of failures then, too.
Huge numbers of failures. The difference now is maybe the transparency, the speed of attempts, and yes, the commercial pressure. But failure was definitely part of the government learning curve, too.
And 2025 has been a real microcosm of this. We had ISSpace's failure, but also launching on the same rocket,
Firefly Aerospace's Blue Ghost lander.
which successfully landed March
Yeah.
2nd, operated for 2 weeks, a big win.
A huge win. Firefly's CEO called it a success for commercial space exploration, and he was right. It showed it can be done.
But then you have the sort of partial successes, or maybe partial failures. Intuitive Machines' Athena lander.
Right. Landed, but off target by about 800 feet, ended up in a crater and tipped
Wow.
over.
Still sent back photos for about a day, though, which is something. And their first attempt, Odysseus, also landed but broke a leg and tipped.
Exactly. So they're getting to the surface, but achieving full mission success after landing is still proving tricky. Even a tip over can severely limit operations.
And we can't forget Astrobotic's Peregrine lander earlier in 2024. That one didn't even get close. Had a propulsion leak, a mission-ending failure right after launch.
Yeah, that highlighted the risks even before you get to the tricky landing part. Space is hard, from launch onwards.
So what does this all mean? It seems like landing on the moon is just incredibly tough, no matter who you are.
It absolutely is. Fine margins, complex systems, harsh environment. But the key thing is they're not stopping.
No, definitely not. Which brings us to the why. Why keep trying despite these very public, very expensive failures? What's the pull?
It's the long game. It's the vision. For ISSpace, for instance, it's about proving the moon can be a source of resources, starting with water ice. They want to show, quite literally, that the moon is open for business.
Mining the moon. That still sounds like science fiction to many.
Maybe. But the potential payoff is enormous if they can unlock lunar resources, initially for supporting further space exploration and eventually, maybe, for use back on Earth. They're betting on a future lunar economy.
And market analysts seem to agree there's something there. Analysis Mason put out a report forecasting over 450 missions by 2033.
Yeah, generating something like, what, 151 billion US dollars in revenue? It's a huge projected market.
151 billion, that's staggering.
It is. But here's the really interesting part of their analysis. The government sector is expected to account for 75% of that revenue.
75%. So it's still mostly government money driving this.
Exactly. Big programs like NASA's Artemis with the U.S. and international partners,
Yeah.
and China's ILRS, the International Lunar Research Station, they're creating the core demand. While Artemis missions have faced delays, the government commitment is strong.
So these private companies, even with failures, are kind of building the infrastructure and testing the tech that governments ultimately want and need.
Precisely. These failures, while costly for the companies, are essentially de-risking the technology for the whole ecosystem, an ecosystem underpinned by massive government investment and ambition. They're providing that proof of concept Goswami mentioned, failure by failure, success by success.
So where's the sweet spot for commercial players then, according to Analysis Mason, if government is the main customer?
They highlighted two key areas, transportation and infrastructure,
Okay, transportation meaning.
getting stuff there. Demand for cargo delivery, especially smaller payloads, is growing. This offers a good entry point for medium-sized companies. Maybe you don't build the whole lander, but you build a ferry service or a component.
Right, and infrastructure.
That's about supporting long-term presence. Think lunar gateway components, habitats, power systems, communication relays, stuff needed for bases or operations in cislunar space. Competition there is relatively lower right now, but the demand is expected to be high. Lots of niches for suppliers.
So it's not just about the landers themselves, but everything around them.
Exactly, building the ecosystem.
Which brings us back to Ospace. Their CEO, Takeshi Hakamada, was pretty frank. This is our second failure. We have to really take it seriously. But he immediately followed with, eSpace will not let this be a setback. Never quit the lunar quest.
That's the mindset you need. Resilience, literally.
So what are they actually doing for missions 3 and 4 planned for 2027? How are they taking it seriously?
They're tackling the sensor issue head-on, strengthening testing and verification for landing sensors, especially LRFs, improving the hardware robustness,
Okay, better testing. Makes sense.
but also adding redundancy. They plan to include more landing sensors, potentially adding LiDAR, which is another type of laser ranging system, and maybe vision-based navigation cameras.
So multiple ways to measure altitude and velocity, cross-checking each other.
Exactly. Building in layers of safety. If one sensor has an issue, others can hopefully take over or provide conflicting data that the system can flag.
And they're not doing this in isolation, right? They're getting help.
Yes, that's key. They've set up an external review task force with experts from JAXA, the Japanese Space Agency, and NASA. And they're getting more direct technical support from JAK, even signing an MU for the Mission 4 lander development.
That collaboration sounds crucial, bringing in outside eyes.
It really is. Sharing expertise, lessons learned, it benefits everyone trying to tackle this challenge.
Now, all these improvements, more sensors, better testing, external reviews, that sounds expensive. They mentioned it could add over $10 million, 1.5 billion yen, to the cost.
It's a significant added cost, no doubt.
But they also said it's not expected to delay missions 3 and 4 or impact their financial forecast. How does that work?
It suggests they likely had contingency built in, or their investors understand this is part of the R&D process for this high-risk, high-reward venture. It's an investment in making sure Mission 3 doesn't fail the same way.
Investing in resilience, you could say.
Pretty much. And it's worth noting Missions 3 and 4 will use a new, larger lander called Apex 1.0. So they're iterating the whole platform, not just patching the sensors on the old design.
Upgrading across the board.
Seems like it. A bigger, more capable platform,
Yeah.
presumably incorporating all these lessons.
Okay, so, summing up. It seems clear that landing on the moon remains incredibly difficult, a real challenge.
No question. Decades after Apollo, it's still pushing the limits of technology and engineering.
But every attempt, even the ones that end in failure like resilience, provides invaluable data. They're not just setbacks, they're stepping stones. Expensive ones, but stepping stones.
Absolutely. Each one helps refine the technology, understand the environment better. It's a tough learning curve, but they are climbing it.
And the drive to get there, to explore, maybe eventually commercialize, it seems unstoppable, fueled by both government ambition and this growing private sector boldness.
The momentum is definitely there. Despite the hurdles, the pull of the moon for science, for resources, for the future is strong.
Which leaves us with a thought, maybe for you listening. As we watch these private companies push boundaries, and as failures inevitably continue to be part of that story, how should we think about success? Does success in this new era of, off-world commerce have to mean a perfect landing every time?
Or is there value, real success, in the attempt itself? In the resilience shown by companies like ISpace, and in the critical data gathered, even from a mission that ends, quite literally, with impact? Something to think about.